Hello students, today I am going to discuss about vibration. In the previous chapter, I already discussed about the simple harmonic motion or SHM. At first, I am telling you about the definition of vibration. Definition: vibration is one kind of motion in which the particles of the system execute SHM or complex periodic motion. That is, when the particles of the system execute simple harmonic motion or complex periodic motion, then we can say that the system vibrates. Okay. Examples of vibrations are the vibration of a string, a vibration of a spring, etc. Now we can classify the vibration according to the nature of motion into three categories. Vibration can be classified into three types according to the nature of motion. First, transverse vibration, second, longitudinal vibration, and third, torsional vibration. Next, transverse vibration. When the particles of the system vibrate along the normal direction of the length of the body, then this type of vibration is known as transverse vibration. It is a three-dimensional vibration. Let a string is stretched along x-axis, then the particle of the string vibrates along y prime axis or y axis. The particles of the string may also vibrate along z axis. That's why this type of vibration is a three-dimensional vibration. Okay. In this case, the wave produced propagates along the length of the string, and the mode of vibration of the particle is normal to the motion of the wave. Next, longitudinal vibration. When the particles of the system vibrate along the parallel direction of the length of the body, then this type of vibration is known as longitudinal vibration. It is a one-dimensional vibration. Example, the vibration of a spring. Let a spring is suspended from a rigid ceiling and a weight is placed at the another end of the spring. When we pull down the weight, then the spring vibrates along the vertical line. This vibration is along the length of the spring. This is known as longitudinal vibration. In this case, the particle vibrates along the vertical line and the spring is also placed along the vertical line. That's why it is a one-dimensional vibration. Next, torsional vibration. When a wire is suspended from a rigid ceiling and a heavy plate is fixed with the wire such that the wire acts as an axis of the plate and the plate is twisted. Then the plate executes to and fro motion. This type of vibration is known as torsional vibration. This is a rigid ceiling and this wire is suspended from the ceiling. A plate is fixed with the wire. When the plate is twisted, when the plate is twisted, then this plate shows the to and fro motion. Therefore, the particles of the wire also executes to and fro motion. This type of vibration is known as torsional vibration. Example of this vibration is torsional pendulum. Next, classification of vibration according to the nature of amplitude of vibration. Classification of vibration according to the nature of amplitude of vibration. This type of vibration can be differentiated into three categories: natural vibration, damped vibration, and forced vibration. Natural vibration, damped vibration, and forced vibration. Next, natural vibration. When a body vibrates with its own frequency and its amplitude always remains constant and no external force acts on it except restoring force, then this type of vibration is known as natural vibration. In this figure, along y-axis we can plot the displacement and along horizontal axis we can plot the time. Along vertical axis we can plot the displacement and along horizontal axis we can plot the time. This graph shows the variation of displacement with time of the particle. In this case, the amplitude always remains constant and amplitude does not decrease or increase with time. This type of vibration is known as natural vibration. You should remember that this type of vibration is ideal one. Now the differential equation of natural vibration is m dou 2x dou t2 is equal to minus sx, where s is the restoring force constant. In case of spring, we can write k instead of s, where k is the force constant of the spring. Now we can write dou 2x dou t2 is equal to minus x by m into x. Let s by m is equal to omega square, where or omega 0 square, where omega 0 is the natural angular frequency of the body, where omega 0 is known as natural angular frequency of the body. Natural angular frequency of the body. Okay. Sometimes S is known as stiffness constant. Solution of this differential equation is differential equation is x is equal to capital A sine omega 0 t plus alpha, where alpha is the initial phase and A is the amplitude. Where A and alpha are constants. A denotes the amplitude and alpha denotes the initial phase. Of the body. Next, damped vibration. When a dissipative force acts on a vibrating body, then its amplitude decreases with increase of time duration. Then this type of vibration is known as damped vibration. The dissipative force is directly proportional to the velocity of the body. Okay. Therefore, the differential equation of the motion of the body is m dot 2x dot t2 is equal to minus sx. This is the differential equation of natural vibration, and minus bv is introduced due to the dissipative force, where v is a constant known as damping coefficient. And damped vibration is commonly shown in our nature. In this case, the amplitude of the body decreases with the increase of time. After some time, the vibrating body stops. Now we are going to solve this differential equation. We can write dou 2x dou t2 plus b by m dou x dou t plus x by m x equal to 0, since velocity of the body v is equal to dou x dou t. Solution of the differential equation is x is equal to a0 e to the power minus bt by 2m cos omega prime t plus phi. Here e stands for exponential. Omega prime is equal to under root of s by m minus b square by 4m square. Here omega prime is the frequency of the vibrating body. A0 is the initial amplitude of the body and phi is the initial phase of the body. Here the amplitude of the body A0 e to the power minus bt by 2m depends on time. When t tends to infinity, then the amplitude becomes 0. That's why after some time the body stops its vibration. When the dissipative force is more, then the time duration to stop the body is less. This graph shows about the variation of amplitude with time. Here amplitude of the body is a factor of exponential. That's why amplitude decreases with time. After infinity time, the amplitude will be 0. When the value of B is less than 2 root over of Sm, then it is known as light damped vibration. In this case, the amplitude of the body decreases with exponential factor with time. That is, amplitude decreases exponentially with time. This is known as light damped vibration. In this case, the damped force is very small. When B is equal to root over of 2 Sm, then it is known as critical damping. In this case, the body or particle moves from its maximum amplitude to its mean position in minimum time. Okay. This graph shows the critical damping. When B is greater than 2 root over of Sm, that is when the damping force is very high, then it is known as over damped motion or aperiodic motion. This graph shows the over damped motion. Along vertical line, we plot the amplitude of the particle, and along horizontal line we plot the time. Now, force vibration. When a periodic force acts on a vibrating body, then the vibration is known as force vibration. Okay. In this case, initially the body vibrates with its own frequency, but after some time it vibrates with the frequency of periodic force. Let F is equal to F0 sine omega t is the external force, periodic force acts on the vibrating body with angular frequency omega. Then the differential equation of the motion is, now the differential equation of the motion is m dou 2x dou t2 plus b dou x dou t plus sx is equal to f0 sine omega t. Solution of this equation is x equal to capital A sine omega t minus phi, where capital A is equal to f0 whole divided by m square omega 0 square minus omega square whole square plus omega square b square whole to the power half. This is the amplitude of the body, and phi is equal to tan inverse minus v0 by omega x0 is equal to initial phase of the body, where v0 is the velocity of the body and x0 is the initial displacement of the body. v0 is the initial velocity of the body and x0 is the initial displacement of the body. Next, resonance. When omega 0 is equal to omega, then the value of amplitude A will be maximum. Then value of amplitude A will be maximum. This is known as amplitude resonance. This is known as amplitude resonance. That is, when the natural frequency of the body, vibrating body, is equal to the frequency of the periodic force, then the body vibrates with its maximum amplitude. This is known as resonance. Now I am concluding my discussion for today. I hope you all understand this topic. Please subscribe my channel and please click the like button. Thank you for watching my video.